all, I'm Saish Palande from TY Electrical. Along with my group members, we are presenting the topic of control of DC motor using transfer function based modeling under the guidance of Dr. G. Vijay Kumar. So let's understand the concept of control of DC motor using transfer function. Control of DC motor using transfer function based modeling involves the deriving the mathematical model of the motor using Laplace transform. The motor's electrical and mechanical dynamics are represented by the differential equations, which are converted into the transfer function relating to the motor speed to the input voltage. So let's understand the simulation overview. So the blocks we have used in these simulations are armature voltage input. For a constant input voltage, that is 220 volt, is applied to the motor. Then second block is the transfer function representation. The third block is torque generation. And the another block is the speed and position calculation. To motor speed is to obtain from the transfer function relating to the torque and velocity. Then the output displayed to the simulation provides motor speed and distance traveled. So let's understand the graphical representation. So in the first graph, it represents the armature current versus motor speed. On the x-axis, there is a motor speed in radian per second, and on the y-axis, armature current. The graph shows a linear relationship between the armature current and the motor speed. As motor speed increases, the armature current also increases. This expected behavior because of the DC motor. More speed requires the more current due to the counter electromotive force EMF. Then the second graph shows the motor speed response. On the x-axis it is the time, and on the y-axis it is the speed. The motor speed quickly rises and stabilizes at 195.3 radian per second, and the speed shows the first rise with the minimal overshoot, indicating a well-tuned system. This means the motor reaches the steady state speed effectively with the good stability.
So, hello everyone, my name is Sai Power and I am going to explain MATLAB programming for computing motor speed and the plotting speed response. So, given motor parameter is armature resistor, armature inductor, back EMF constant, DC supply, and load torque and the damping coefficient. So the value of the armature resistance is 0.5 ohm, armature inductor is 0.03 Henry, back EMF is 0.8 to 20 voltage DC supply, and the load torque is 100 Newton meter, and the damping constant is 0.1. Now steady state speed, by using the omega m, we use the armature current equation and the back EMF equation. So the armature current equation is given as the IA is equal to load torque plus the damping constant into the omega divided by the back EMF, and the back EMF equation is E is equal to V minus IA into RA. Now we solve the equation of the omega m. For the output for the motor speed is calculated in the radian per second. Now generating the range for the plotting armature current versus speed, we take the omega range and the current range, armature current range. It is the external range for the visualization, and the armature current range is computing the armature current. By using this line pace equation, now we plotting the armature current versus speed. On the x-axis there is motor speed and the y-axis is the armature current. Now we take a time constant for putting the graph of the speed response as in the first order system. This is the time response for the motor speed. Now on the x-axis there is time and the y-axis there is speed, and the title of the graph is motor speed response. Now this overall is the code for the motor speed, plotting the speed response, as well as we plot the armature current versus speed. Now run this code. So our motor speed is 195.35 radians second. This is our armature current versus motor speed graph, and this is our motor speed response. This is the speed and this is the time second.
Today I am going to simulate the model of the control of DC motor using the transfer function based modeling in the MATLAB simulation. So for that, very firstly we have to take the armature voltage uh, as a 220 volt. So this is the constant DC voltage source we have to take. So this voltage is fed into the summation block 1, which processes the input voltage. So we are going to take the yeah. So this is the summation model. This summation model is mainly used for the to process the input voltage. So then we are going to take further the transfer function model. So this transfer function model uh, is represents the electrical circuits of motor. The inductance EL, which is 0.003 Henry, and the resistance R is a 0.5 ohm. So this block converts the input voltage into the armature current. So further we are going to take the generator torque Tm. So this is the constant we are going to the K 0.8. We are going to take the 0.8. So this IA of S is multiplied by a torque constant K of T is equal to 0.8. So this gives a generated torque T M of S. So next we are going to take the mechanical system representation, the transfer function again. So okay, so this is again we have to take the sum model. uh, okay, so further we are going to take the transfer function model. So yeah, so this again this generated torque is passed through the another transfer function. So this transfer function represents the mechanical dynamics of DC motor. So the inertia is 0.0167 7 yes in kg meter square, and the damping coefficient is a 0.01 Newton meter per second. So this output of block is angular velocity omega m radian per seconds. So for the feedback and integration, we are going to take the integrator block, which is a 1 upon s. Okay, so this integrator block, the velocity output omega m is fed into the integrator block 1 upon s. So this block calculates the position theta of s, and of and it is a feedback loop is present to stabilize the system. And this and we are going to take the summation block number 2, adds an external disturbance 100 to the system. So this gain is adjust the signal scaling.
Hello everyone, my name is Prem Manoj Moe, and today I will explain you how to simulate the to control the DC motor using transfer based modeling. So up to integrator Samartha explaining well. As now as we move forward, we require to display to see the output in values, and to see the waveforms we require scopes. So let's move. So the after taking scope, we will give two inputs. First is the speed response of DC motor, and other is a distance response of DC motor. So simply double click on the scope and see the results. Run, and there is showing two graphs. First graph is a speed response of DC motor, and second is a distance response of DC motor. And to see the values, we simply add the displays over here. After adding the displays, we simply go to simulation and run the system or simulation and see the values. So speed of our DC motor is 195.4, and in graphical representation also the second graph is a speed response of DC motor. The highest or peak value is a 195.4 near to. to 100. So in that simulation also, after the integrator we will get the value which is also called as a distance response. So we will get 2146 as a distance of a DC motor, and in graphical also, in first graph if we see graph is goes beyond the 2000, so it is verified also. So this is all about our simulation. So thank you.
So, in a conclusion, the simulation successfully models a DC motor's dynamic response using transfer function. The results indicates a linear relationship between armature current and the speed, a stable motor speed response with a quick rise time. The control system effectively regulates the motor performance. So we have selected this function based modeling because of to analyze system dynamic without solving differential equations, and it helps controllers like PID and lag lead compensators for stability, and it also allows MATLAB simulations to visualize the motor behaviors. Thank you.